evening. My name is Catherine Paisley. I'm the Vice President of Science Education and Science Experience here at the Ontario Science Centre, and it's my pleasure to welcome you to Great Conversations tonight. Can you a show of hands of people who've come to other Great Conversations? Oh, that's great. And I'm assuming most of you, all of you have been to the Science Centre before, but have we got anybody this is their first time to the Science Centre? A couple people, welcome, thank you. Oh, well, we're glad that you're here, and hopefully this is the first of many visits. So before we continue with tonight's event, I would like to acknowledge that the Science Centre is located on sacred land that has been the site of human activity for tens of thousands of years. This land is the territory of several Indigenous nations, including the Mississaugas of the New Credit. The territory was the subject of the Dish with One Spoon, Wampum Belt Covenant, an agreement between several nations to peaceably share and care for the resources around the Great Lakes. Oops, excuse me. Today we acknowledge that we are settlers living here on this land, and that as settlers, we owe respect, restitution, and reconciliation to these systematically injured Indigenous communities in the territory more recently known as Canada. Our Great Conversation Speaker Series brings leading global experts to the community to share their thoughts, ideas, and perspectives on a wide variety of topical issues, which we hope will provoke dialogue that continues long after the event ends. Tonight, we are honored to have American physicist and Nobel laureate, Dr. Rainer Weiss, here this evening as part of the Charles Darrow Lecture Series, presented in collaboration with our friends, the Royal Astronomical Society of Canada, Toronto Centre. Dr. Weiss received the Nobel Prize in Physics in 2017, and his groundbreaking discovery has opened an unprecedented window into the cosmos, launching a new era of astrophysics. You all know that, that's why you're here tonight. We'll be treated to a formal presentation in which Dr. Weiss shares the key elements that led to the detection of gravitational waves, followed by a one-on-one conversation with our moderator, Dr. Sara Seager, an astrophysicist and planetary scientist from MIT. And then we'll round out the evening with a Q&A with all of you, so save your questions, please. As I mentioned earlier, tonight's Great Conversation event is presented in collaboration with the Royal Astronomical Society of Canada, or RASC. For 20 years, we've partnered with the RASC to provide invaluable astronomy programming and space events such as solar observing and star parties. And perhaps some of you have been here for those, and if not, I would encourage you to come. They're both outside in our telescape. Tonight's event is another example of our continued collaboration, which aims to engage and educate the public in space sciences. At this time, I'd like to call upon Dr. Ralph Chu, President of RSC Toronto Centre, to say a few words. Thank you.
Thank you, Catherine. Good evening, everyone. The RSC Toronto Centre is Canada's largest local astronomy club. We're part of a nationwide community of over 5,000 amateur and professional astronomers. In Toronto, we have just over 800 members in our local organization, and we have quite a few of them here tonight, which is very nice. I hope that you will enjoy this talk, which is the second of the Charles Darrow Lecture Series. And to talk about that, I'll call on Dr. Sara Seager to come up and just chat about the lecture.
Thank you.
Good evening, everyone. I'm just here to give you a brief background on the Charles Darrow Lecture Series. As you just heard, my name is Sara Seager. I'm an astrophysicist from MIT. It's amazing I get to be an astronomer for my job. Well, I got my start in astronomy at the RSC. I must have been about 5 years old when my dad took me to one of the star parties, and I saw the moon through a telescope, and wow, I mean, I just had no idea it was like a whole other world. When I was a teenager, I joined the club. That's when the meetings used to be held in downtown Toronto, and I could walk from my home, and I was able to be a part of the RASC. I started the Charles Darrow Lecture Series in part so I could give back to the club, and to thank all of you, all the volunteers who continue to do all the outreach events. And I know a lot of children today go to those events still. So a few years ago, the RSC invited me back as an honorary lifetime member and as a keynote speaker at the General Assembly that was held in Thunder Bay. And for our honored guest, I just wanted him to know Thunder Bay, it's on the north shore of Lake Superior. I mean, if you live in Toronto, it seems kind of far. So the most amazing thing happened when I got to the meeting. My hostess dropped me off at the reception before the talk, and it has nothing to do with astronomy. But I met Charles, and we became instant friends, later on followed by a whirlwind romance, and we're now married. So I started the Charles Darrow Lecture Series partly because I was just so grateful to have met Charles and got married, and also to recognize his contributions to the club. He was president of the Toronto Centre when I met him, and he has been on the council for many years before that, and now serves on the council as past president. So after Charles and I got married, he moved to Boston, and he had to leave Toronto and all of you, unfortunately. And what became part of his new normal as he travels with me and goes to events at MIT was meeting all these fantastic, amazing scientists who are also wonderful communicators. And so our goal with the Charles Darrow Lecture Series is to bring some of the people. It's actually for Charles. He chooses the speaker and hosts the speaker, and we bring the speaker to all of you. Now, in February 2016, we all know, or you'll hear about the great announcement of the first gravitational wave discovery. And Charles immediately wanted to invite Professor Weiss. I told Charles Professor Weiss is a little busy with the discoveries, and then later he was busy getting his Nobel Prize. So we're actually thrilled to be able to finally bring him here today. And with that, I will call on Paul Delaney, Professor Paul Delaney, to introduce our speaker tonight. Thank you.
Thank you very much, Sarah. I am the second vice president of the Toronto Centre, and it's certainly my pleasure to welcome you all here this evening and to do the honours of introducing the guest speaker. Rainer, or Ray Weiss, was born in Berlin, Germany, September 29th, 1932. He's an American physicist, receiving his PhD from the Massachusetts Institute of Technology in 1962. He has been a faculty member at MIT from 1964 to 2001 and is an emeritus professor there since. And he is acclaimed for his contributions in gravitational physics and astrophysics, and has been instrumental in a number of, shall I say, earth-shattering, universe-shattering discoveries in his time with MIT. While he is best known for inventing the laser interferometric technique, which is the basic operation of LIGO, he is no stranger to problems in cosmology, and is well known for his pioneering efforts in a wide range of instrumentation developments. As just one example, Ray was the co-founder and science advisor to the NASA Cosmic Background Explorer satellite mission that operated from 1989 to 1993. The mission is often cited as the beginning of cosmology as a precision science, as that satellite verified the near-perfect black-body radiation spectrum of the cosmic microwave background radiation, hosting a temperature of about 2.73 degrees Kelvin, just a little bit above absolute zero, as well as identifying many of the anisotropies, the irregularities of that background. As you would expect, Ray's awards are numerous. No, I'm not going to list them all, and very impressive. But arguably the pinnacle came in 2017 when he was awarded the Nobel Prize in Physics, along with Kip Thorne and Barry Barish, for, and I quote, decisive contributions to the Laser Interferometer and Gravity Wave Observatory, LIGO, detector, and observation of gravitational waves. It is the RASC's great pleasure to have Ray Weiss deliver the 2018 Charles Darrow Lecture entitled Exploration of the Universe with Gravitational Waves. Ray.
Wow. Oh, wow. I mean, all this stuff, you know, about... let me make sure that I don't disappoint Charles Darrow with this talk. You have to keep looking at him. If he looks like he's scowling, you better tell me that, okay? Anyway, I'm going to talk to you about gravitational waves, but I also want to say something first. As you saw in the beginning of this talk, before we got on the stage here, there were many little clips that you saw, and it turns out there were an awful lot of people who did this, not just me. And I want to show you, as you see in the listing of the, whoops, somebody's got to turn on the screen here. We got to get these slides on that screen. There we go. Okay, good. Thank you. Anyway, I speak on behalf of something called the LIGO Scientific Collaboration. Let me show you that collaboration. It's a picture with all the different people in the universities and centers that were part of this. And I'll point out to you something right here. There's a maple leaf. How about that? And that is the University of Toronto has a group that has done data analysis, and along with the Perimeter Institute, which is not too far from here. So Canada plays a role in this, and I hope they will play a continuing role in it. So what is this all about? Well, first of all, many of you who have been in high school and maybe have taken a course in physics have seen, and this is Isaac Newton, of course, and seen the representation of gravitation given in this very simple formula, which says the following. It says that there's a gravitational force, and that force is somehow dependent on a constant, which we'll not worry about, but is very importantly dependent on the amount of mass an object has, and attracting another mass, which has mass 2 and mass 1. And that force gets weaker and weaker the further apart the two masses are. That law, by the way, is enough to explain almost everything you know about gravity. Almost everything. It got us to the moon. It worked for Newton to explain why it was that the moon was going around the Earth the same way that an apple was falling to the Earth. That's a very profound thing that Newton discovered. And the thing is that this law just works for everything. Why do we need anything else? Well, it turns out you do. It doesn't work for certain situations. It doesn't work for very fast-moving objects, things that are moving near the velocity of light. It doesn't work for things that are, where the fields are very strong, where gravity is very strong. And it doesn't work in the most important place. It doesn't allow nature to have any way to communicate information via gravity. Let me explain that to you. When something, let's suppose somebody took the sun away. Right now, it's hard to do that, but just imagine, okay? Somebody took the sun away. It would take you and me about 9 minutes or 8 minutes to know that after the fact. Why? Because it takes about that long for the light from the sun to get to the Earth. Now, in Newton's theory, if you took the sun away, gravitationally, we know what we're doing. Here's the sun, and we're going around the sun in for effect, ellipse, but let's call it a circle, okay? We're going around the sun. And you would keep going around the sun. In Newton's theory, we would immediately know that the sun had been plucked away, because what would happen is, here, let's say the sun gets, here we're going on our arc, and then you take the sun away, and you would go off on a tangent in that arc. That would happen instantaneously in that theory. And that's not allowed by Einstein's first ideas about special relativity. Things cannot move, and that's information, cannot move faster than the velocity of light. So that's something that's very wrong with this theory. Now, you say, oh, it doesn't matter much. Well, it turns out, how many of you have GPS on your little cell phones? Most of you. That GPS wouldn't work if you didn't take that into account. Okay? So it turns out that, and it comes in several guises. So here then is Einstein's theory. There's Albert. This is a little bit of an anachronism. He's much older in this picture than that equation. The equation is older than he is. I'm sorry. I said it wrong. I mean, he is at the end of his life. This equation was done when in 1915. And this is the replacement for that equation. Now, let me just tell you what's in that equation. You know, you and I are not going to solve that equation. Computers can barely solve that equation now, but they can. What this says is something quite spectacular. It says, this is another way of thinking about gravity. It says the geometry of space and time, which is what this symbol is somehow proportional, but this is just a constant, an 8 and pi, that you understand, but it's proportional to the distribution of energy and mass in the surrounding space. In other words, the geometry of space and time is determined by the distribution of matter that is placed in it. And there is no more gravitational force. It's gone. Let me try to show you an example of that as best as I can. This is how many of you know what a jungle gym is? I mean, many of you have been kids, I'm sure. And you may have played in jungle gyms at some time. I come from New York, and every park has a jungle gym in it. Big set of parallel bars in all 3 dimensions, bars this way, bars that way, and they make a big matrix. And kids love to jump around inside of it, and that's what I want you to imagine. Now, we made a jungle gym, and what you now have done is you've taken a cut through the jungle gym, a 2-dimensional cut. So that's what you're looking at in this picture. And these are the bars of the jungle gym in 2 dimensions. And out here, it looks pretty flat. Everything looks like the jungle gym. But when you get closer to these 2 objects, that one is the sun, and that has a big effect on it. We'll get to that in a minute. And then there's the Earth, which also has a little tiny effect, but it's there. So these things they're doing what that equation says. They have distorted space. Space is now distorted in this 2-dimensional picture. It's become curvy. It has done another thing too, these objects have done something else, which is not depicted in this picture, but they have made it so that the clocks, if you have clocks and you put them all out here far away, every one of these intersection points, you put a clock. Imagine clocks everywhere. I got bored putting one in if I had to do it. But they all keep the same time at the same moment of time. That's what the clocks will do. The clocks that get close to these objects, which are in this curved part of geometry, they don't go at the same rate as the clocks out here far away from them. They go a little more slowly. So you have this very interesting phenomena. Space is distorted by these objects that you put into the space, and time is dilated or distorted also. You need to have both things happening. And here's another example where the GPS that's on your little cell phone has to take that into account, otherwise you wouldn't get home. So it turns out the clocks out there on the satellites that are making the signals that give you the GPS signal are keeping a different clock rate than the ones on the ground here. And that's quite essential to the whole idea of general relativity. And now what is the thing here's the nice way that John Wheeler, who was one of the people who followed Einstein, said, what space and time do now, it makes those objects that you stick into this geometry of space and time, it tells them how to move. In other words, the geometry is no longer a force. The geometry itself is the thing that determines, and the way the time is kept tells things how they are going to move. There is no longer a force. Okay, this theory then predicts something which is gravitational waves. And I'm going to show you one in a minute. And this is a gravitational wave, which I'll make this into an animation in a minute. But again, what are gravitational waves are generated in this theory by masses that get accelerated. In other words, and they have to be non-spherically symmetrically accelerated. In other words, if you take a great big balloon and blow it up and let it collapse and spherically symmetrically, it won't radiate gravitational waves. But a thing where you smash things together like that, or 2 things that are going around each other like this, they are not spherically symmetric, and they will radiate gravitational waves. So that's the first law of gravitation as comes out of how you generate the waves. And so it turns out that what are the ways the waves move? In other words, the kinematics of the waves. That's a fancy word for how they do things. Well, they propagate at the speed of light. That was the assumption that Einstein made. And at the time, it was a guess that he made. But now, and then you'll see in the course of this lecture, we know exactly that they move at the speed of light. Better than one of the best measurements that's been made. We now know gravitational waves do travel at the speed of light from experiment. I'll tell you about that later. And now, the thing that's a little more difficult with the gravitational waves, they are transverse waves. What does that mean? You saw, probably when you came into the lecture, a pebble being dropped into a pile of water. And that is the wave that's not traveling in the water, like if you make a little puddle in your bathtub and you drop something into it. Those are transverse waves, because what they do is they move in this direction, but they're doing their business, the thing that makes them look wavy, they do it up and down. So that's perpendicular to the direction in which the wave is propagating. These waves, gravitational waves, do their business perpendicular to the direction in which they're moving. Very much like electromagnetic waves, like light and radio waves. They do the same thing. So let me start this up, and you'll see what a gravitational wave actually looks like. In other words, this is a bunch of masses that have been distributed in space If you can see this red square that's around that one in the middle, that's where you're standing watching this wave coming at you out of the picture. So let me see if I can get this moving. Yeah, good. Now, you get a little dizzy if you look at it very hard, but don't worry about it. So there are a couple of things I want you to notice about this. There are you're standing there. Nothing much seems to be happening to you, but you'll notice that in one dimension, perpendicular to the direction of the traveling of the wave, which is out at you, there's stretching going on of space. While the other dimension, let's say up and down, there is expansion of space, and it keeps flipping back and forth. So now it's expanding, and you just look in the two directions, perpendicular direction in which the wave is moving, there's expansion in one dimension, contraction in the other, and it keeps flipping back and forth. Do you see that? Good. Okay, that's one property. The other property is that, this is now a little more subtle, you'll notice that the dots, let's take you again, and let's look at the dots next to you. That guy and that guy, they're not moving very much. But take a look at these two. This guy that's very far away from you, and that guy who's very far away from you. They're moving a lot. So it turns out there is something constant in that picture. It's very much like when you stretch a rubber band in your hands, and you had made marks on the rubber band and you pull it. You'll find out that you're making a pattern of something that's called a constant strain. What's a strain? We'll talk a lot more about strains. But they are a change in position, the change in position of that dot with respect to that one, divided by their separation. That change in position divided by their separation is the same all along those lines. Some are negative, some are positive, depending on whether it's expanding or contracting. That quantity, the strain, change in length divided by their separation, is the quantity that is the thing that's measurable. And that's what you trade on when you try to measure a gravitational wave. Are you with me? Who's confused? Somebody. Well, okay, you're not admitting it. All right. All right, I'll keep going. It gets worse. Here's a guy who was the first person really. There had been measurements, and by the way, I'm leaving out a lot so I can stay on time. There were measurements made early on by people by looking at double stars that actually saw some evidence for gravitational waves before the direct measurements were made. And that won a Nobel Prize also. Hulse and Taylor, those two people won a Nobel Prize for looking at a binary neutron star system. It's two stars that are made of nuclear matter, and they were radiating gravitational waves. They figured that out by looking at their orbits. But this is the first guy who was trying to measure these effects that I just showed you directly. And this is Joseph Weber, who was a professor at the University of Maryland. And here he is with his laboratory. In his laboratory, there he is. He has a big aluminum bar here, a big long bar like that. And you can see it's kind of bigger than he is. There he is. And what he's attaching to it is strain gauges, little gauges that measure the distortion of that bar. And the idea he had was a gravitational wave would come along, do what you saw in that picture, stretch it in this dimension and compress it in this dimension, and cause the bar, if it goes through quickly, to sing like a xylophone. The gravitational wave was much like bopping that bar with a hammer. And what would then happen is that he could measure the motion of the bar with these little gauges. And there's a big vacuum system in which he put this device. Well, it turned out, to his misfortune, in 1969, he wrote a very, very famous paper in the field of gravitation saying that he had made a discovery of gravitational waves. And it was in one of the more prestigious magazines of physics called Physical Review Letters. And it turns out that he had seen it with what he had done. He had put one of those bars in Chicago. He put another bar in his laboratory in Maryland and had another one in a golf course about 8 miles away from his office. And all three of them got bopped simultaneously. And they would get bopped sort of simultaneously 3 times a day. And he said that was evidence for gravitational waves. Well, a nice thing about physics, or a nice thing about science, is that other people they read this and they said, wow, this is really interesting. And so this is not a very difficult experiment to do. You can imagine even doing it yourself, I bet. Yes. And maybe, okay, you need to know a little bit of electronics. I mean, not, okay. And you have to have a vacuum system, but it's not a big deal. And so what happens is that a lot of people in the world, about 10 other groups in the world, did the experiment and they saw nothing. Absolutely nothing. And so another idea became important to try to do this. And let me show you this idea. This is actually the idea that was LIGO. That's the thing that led to LIGO. And let me walk you through this one. This is a little animation you're going to see in a second. But what it is another way to do the same kind of a measurement using the time it takes light to travel between things. So for example, what is this little gadget? A gravitational wave is going to come down on this. It's going to stretch the space, let's say, in this dimension, and it's going to contract the space in that dimension. Then it'll flip. So these are the two mirrors. Up there's one, there's another. And here's a laser. It doesn't look like a laser, but it'll work as a laser in a second. That laser sends light to a thing that's called a beam splitter, which divides the light. Half of it gets reflected and goes to that mirror, and then comes back again. The other half goes through this beam splitter and goes to this one. It's transmitted by this, hits this mirror and comes back again and is reflected. And so two beams, as you'll see them, come to this detector. Let me turn this thing on so you'll see what I'm talking about. Okay, so wherever you see red, which is where there's light power, light, and the wiggly thing is the electric field in the light. That's the wave in the light. And you can see what's going on. What you've done is we've made the light spend exactly the same time in both arms, and the light then cancels out. You can see the two waves have opposite signs, and they have no light. There's no red. No light goes to the photodetector. Now, you do the thing which a gravitational wave does. Stretch one arm, shrink the other, and keep doing it, and you'll see when they are not equal anymore, you do get light to the photodetector. And there's nothing more to the whole idea that LIGO was based on than that. In other words, you set a trap for a gravitational wave with light, and what you do is you make it so that the time it takes light to go in these two arms, we were talking about identical, then the lights cancel to the detector. The cancellation gets ruined when the gravitational wave comes in and stretches one arm, makes the light go a little longer in one arm and shorter in the other arm, and that's how you get light at the photodetector. That's the basic idea of LIGO. Okay. Well, along comes Kip Thorne, who spoiled the show. Okay. And what happened, here's Kip Thorne. He was a pretty dashing theorist. This is many years ago. And he said to us, all of us, and he was a guy who had been studying this with his group, that if you are going to get into business with this kind of a thing, you've got to measure strains, and that's now the formal definition of a strain, like I told you. It's a change in length divided by a length, and that has a symbol. It's called h. We'll use h in a few places. And now comes the part of the talk where I have to trust you. This says that what Kip was saying to us is if you're going to detect something with a device like this, you're going to have to look for strains that are smaller than 10 to the minus 21. Now, what does that mean? How many of you are baffled by this exponential notation? I really want to be honest with me, please. A few of you. Okay, let me just say what it is. I mean, so that you and I are in the same wavelength. Okay? 10 to the minus 21 means it's a decimal point, 20 zeros, 0.0000, 20 times then a 1. That's one way of writing 10 to the minus 21. Okay? So when you want to tell somebody what's a number, it's very nice to use this exponential notation. For example, 100, the number 100 would be 10 to the 2. That's 10 times 10, that's 100. Or if you put in the denominator 1 over 10 times 10, that's 10 to the minus 2. That's 100th. I wish the newspapers would use this kind of notation. You would then, instead of talking about trillionths and billion trillionths, you never know what the hell they're talking about. This is a way you can know exactly what's going on. If somebody says the budget of Canada is 10 to the $13, you say, hey, that's kind of big, you know. All right. Or budget of the United States is 10 to the 14, much too big. Okay. So anyway, Kip came along and said, you're not going to get anywhere unless you measure something this small. And what does that mean? If you build something that's 4 kilometers long, like that interferometer I just showed you, that device, you wind up at the end moving only, remember delta L over L, 10 to the minus 21, you multiply that by 4 kilometers, you wind up with 4 times 10 to the minus 18 meters, which is, as that initial thing said, about 1,000th the size of the nucleus of an atom. And that is very, very small. And I want to give you a feel for how small it is. And that's the reason it took so long to make these measurements. The ideas were pretty straightforward. But the part where you got into trouble is right here. Because what it says is this: if you're going to try to make a measurement of 10 to the minus 18 meters, that says if you try to figure out in the terms of the wavelength of light, and the wavelength of light is about 10 to the minus 6 meters, a millionth of a meter. So it turns out that you're dealing with 10 to the minus 12 of a wavelength. You have to figure out how to measure with light something that's 10 to the 12 times smaller than the wavelength. That was challenge number one. But you're not done yet. You also have to figure out that those mirrors that you placed, those mirrors you saw in that picture of the animation, they can't be moving more for other reasons than the gravitational waves, than about 10 to the minus 12 of the vibration of the Earth right here. In this room, you're not really so close to the ocean, so it's not crazy to say that if you put a seismometer on the floor here, you would find out this place is shaking by about 10 to the minus 6 meters. Everybody in here is wiggling up and down by 10 to the minus 6 meters. I'm surprised you're not seasick, okay? But you have to deal with that. So it turns out that's a much harder part of the problem. How to get the mirrors that you are now using as a way to tell you when the gravitational wave has come by, that they can't be shaking more than the Earth is shaking, and they can't be shaking, they're shaking this much smaller, 10 to the minus 12 times smaller than the motion of the Earth. And that was a big challenge. So here's the first, I'll quickly show you how we went at the business of getting the light. I won't go through this at all. You could ask me questions about it later. But the idea is, here is what you saw already. Here's the laser. There's the beam splitter that I showed you before. And here are these distant mirrors. That's what you saw in that animation. There's some new mirrors in here. There's a thing that lets the light bounce back and forth many times in this arm, and then there is another mirror in here. And what all of these mirrors do is makes it so that if you have 10 watts coming out of the laser, there is 5 or maybe 1 kilowatt of light in here, and there is about close to half a megawatt of light in these arms. And that's ultimately how you get the sensitivity to make the measurement. I'm only showing you this because those of you who really want to know more about this can ask me to tell you about that picture in the questions. This is a noise budget. I don't want to talk about it here. But I want you, if you're interested, ask me to show that picture and I'll tell you about it more. So let me now talk to you about the systems that did this. So here are the LIGO detectors. There are two. One in the United States is near New Orleans in Louisiana. Another one is up in the Pacific Northwest. Here's not too far from British Columbia. And then here is another detector called the Virgo detector, which is near Pisa, Italy. And then there's another detector, which is a research detector in Hanover, Germany. That's a shorter detector. This one's about 3 kilometers long. These two are both 4 kilometers long on an arm. And 2 other detectors are in process of being built. And we'll understand in a minute why it's important to have more detectors. But the Japanese are building one, and the Indians are going to build one. Okay, so let me quickly show you what LIGO looks like. A very quick tour of LIGO. This is LIGO in Louisiana, looking down on it. And yeah, there it goes. So this is LIGO up in the Pacific Northwest, and it's a desert. Here, all the vacuum and the tubes and laser lights are all inside this metal tube inside this concrete thing. Here's that tube in which this is a very high vacuum in here to keep the light from being scattered. Here are people working on a laser table in the central building. And here's the control room for LIGO in Louisiana. And here are people learning how to run the instrument. And that's actually not trivial when you start looking at the problems. Okay, here is a picture which I just want to show you. I won't describe more than to say this is a history of LIGO, the first go with LIGO. And what it is this is the picture of the sensitivity, how small a distance so you can measure, and as you work your way down, it's smaller and smaller and smaller. And this is as a function of frequency. Here's 100 hertz. So the piano's, middle C on the piano is about right there. And there's a very low frequency, about 10 hertz. And here's 1,000 hertz. And this is a history of from 2001 to 2006. We started with the instrument way up here, being crummy as hell. And eventually, every year we improved it. We got down to here. This red one is about as good as well as we did with the initial detector. And you can see buried in there is a little theoretical curve, which we didn't quite make it at low frequencies. But at high frequencies, we certainly made our design. And we saw absolutely nothing. But we saw a good nothing. There's a very big difference between bad nothings and good nothings. A good nothing is we understood why we didn't see anything. All the things we saw were the noise in the detector, and there wasn't any excess noise. So we went back to our government and said, we've got an instrument that's working, but we didn't see anything. We'd like to make it better. And what we did, I won't go into all the reasons, but we improved the isolation from the ground noise. And we built something called Advanced LIGO. And Advanced LIGO has some very fancy things in it. It hangs, for example, the Earth is attached to these springs up here, and one way here's that mirror, which is the suspended mirror, and each one of these is a pendulum. That's another pendulum, another pendulum, another pendulum. You can go home and build this for yourself. Just take a cup, hang it by a thread, and hold it in your hand up here. And you'll notice the following thing. At low frequencies, and a pendulum, the top, which is the ground, moves along with, they move together. The mirror and move together with the motion of the ground. But if you move this very quickly, this thing doesn't move at all. In other words, it moves a little, but very little. And that's the idea of doing isolation. So that was one idea that we had to do. And then this thing up here, I won't describe to you. I'll just tell you what it is. But it was quite fundamental to being able to make the detection. It's very much, how many of you have ever played with headphones that people wear on airplanes, which kill the sound in the airplane, and that you can hear the music in the other? Okay, that's the basic idea. And the way that works is that in the airplane, what happens is there's a little microphone in that headphone that picks up the noise of the airplane. It takes that and flips it around, turns it upside down, and puts it into the headphones, so it cancels the airplane noise into your ear. That's the way that works. That's the same idea here. You measure the ground noise with a seismometer, and you push on a platform to cancel the motion of the Earth. And you do that several times. And those things were the absolutely critical things to make LIGO make a detection. So here's the detection that was made almost as soon as we got this instrument running. We saw this. And what is it? Well, let me tell you what we see here. What you're seeing is, you're seeing a signal that was seen in Livingston, that's in Louisiana. This is time, and that's the strain right there. And you can see these units of strain are about just what Kip said it would be, 10 to the minus 21 times 1. And then, let me say, and this is a signal seen in the Pacific Northwest, at Hanford. And most of this is junk. This is all junk. But then something comes out of the junk. It never gets beautiful, but it gets much bigger than the junk. And then after this, it's all over. This is junk again. If you look over here, it's the same sort of story. And let's superpose these two. You superpose them, and you see that they look similar. They're not identical because the noise isn't the same. So here's the junk. This, again, time, strain. And now you can see that the two signals of two, they're almost the same, but they're not identical. And you had to do something very interesting. You had to shift the signal that came from Louisiana so it would be on top of the signal that is from Pacific Northwest. Why? It turned out whatever this was hit Louisiana first, came through the Earth, and then it wound up in the Pacific Northwest. And the delay is about 7,000th of a second. Wow. So we see the same signal in two places, delayed by 7,000th of a second. That was very exciting. And now, another way to represent this, you've already heard this, but I want to talk about it a little bit. There's another way to represent this signal. And another way to represent it, here it is again. This is time. And here's that signal again. And these are in these two places. But now there's another representation of the signal. This is frequency, the frequency of the signal, the sound it makes. And for example, here's the middle of the piano. See, the middle C is right there. This is sort of the bottom of the piano. And here this is sort of, the brighter this is, the more of the energy there is of this signal at those frequencies. And now you have a frequency representation of it, and now we can listen to it. But now you've already heard it, and you're going to hear it again now. Okay, that's not very exciting. Boom, boom. It's over with very quickly. So we pulled a fast one on you. We changed the frequencies by doing some trickery. And now you can hear it. It's a chirp. That's what it is. And now comes, what is it? Well, here is another piece of the miracle of this whole business. At the same time as people were building these detectors that could do this, other people were doing solutions of the Einstein equations with numerical methods. And that took for many, many years also. It was one equally difficult problem. And here is what we think it is, and we're pretty sure of it. It looks like, and you're going to see this is an animation. This is a real output of a computer. It's not, an artist didn't draw this. This came as the computer output. And what you'll notice is that these are the idea is they're two black holes, and some of the things I showed you in that picture of curvature and the time being changed by strong gravitational fields is in this picture. Wherever the colors are, where the colors get dark, the time has gone to very much longer times. In other words, where it's red, the clocks have really slowed down. And these little arrows are the stretching and curvature of the space. And here are these two black holes getting closer and closer as a function of time, which is over here. You'll see this get slowed down as they get quite close together. And you'll see a storm, a real storm in this two-dimensional picture of this, what happens to space and time. You can look in here. Time has almost stopped. Oh, there's a black spot. Time has come to a stop. And here, the curvature of space is getting unbelievably strong. And here you have now taken those two black holes and you've made a new one. And now what happens is things calm down, and these gravitational waves, which are going off like the thing in a pond, they are then the things that we detected. That model, that picture, is a picture of what we saw. And we then saw more of them. And that, well, before I say that, I want to say something about, we had a press conference in February of 2016, and I was in the subway in New York City. I was going to give a talk someplace, and I saw this advertisement, the one behind me. Let me read it to you. This is in the subway, mind you. It says, "Scientists found gravitational waves in outer space. If only it were that easy to find an apartment in New York City with a walk-in closet." I mean, imagine that, a scientific discovery that gets sort of into the public mind almost immediately. Or here's a thing that was in the New Yorker magazine. These two birds, this guy talking to that guy, he says, "Was that you I heard just now, or was it two black holes colliding?" This was sort of a week after the announcement. It was sort of amazing. And I can tell you, I've talked to people about this, and what it is that Einstein is a name that when you go to school, everybody knows Einstein as a scientist. And most kids know about black holes. They're terrible to be near. You don't want to go near one. So they get out of the comic books. So everybody knew what this was. So here are other black holes that we saw right away, and many of us only began to believe the thing after we saw. That's the first one. The one we were talking about is this one. This is one that happened a little bit later in October. This was one that happened in December of that year. There's all different masses. The mass is over here, and the amount of mass that's lost to gravitational waves is given over here. So we saw more of them. Now, the most interesting thing that happened later was that the Italian detector, when it got on the air, eventually saw it too. And this is now 3 detections. Again, and this is now what is so important about that is this picture of where in the sky might this black hole have lived. And this is sort of a picture of the sky, a map of the sky. And with LIGO alone, you can only tell sort of within a big uncertainty, this banana-shaped thing, where in the sky the two black holes are. Because we only have this timing between, you can't point these things. But by adding another detector at a different place, like Virgo, you could narrow this down. So instead of 1,000 square degrees of uncertainty, you had about 30 square degrees of uncertainty. Still, for astronomers, that's a lot. But it's much, much better than telling an astronomer, go look in 1,000 square degrees. They look like you're a madman. You know, how am I supposed to do that? Okay, so the next big thing that happened is this. This is a completely different thing. And this is the thing that turned out to be very recent. This happened in August of 2017. And what it is you can see now that you're a little trained in this business, here is the gravitational wave signal we saw as in frequency again. And you can see what it's doing. Here's time. And here is the amplitude of the signal as being the brightness. But you'll notice it lasts a long time. This is minus 10 seconds. This is 0. So 10 seconds from here to there. And now this is about 200 hertz. So this is middle C again. And it goes way off. But now comes something spectacular. Let me play this for you so you can see. It's a very different kind of source. Yeah. Okay. That's a real chirp. Those are 2 neutron stars going around each other, doing the same thing the black holes did. But this had another really important feature associated with it. And that is that here is a gamma ray satellite, the Einstein satellite, which was flying and measuring at the time. The end of the chirp is right about there, and you can see this line going up there. And about 2 seconds later, they see a gamma ray burst. And people had thought for years that neutron star collisions would make gamma ray bursts. And there it is. And now here we have this proof that gravitational waves travel about the same speed as light, because this source is 140 million light years away. And it's only 2 seconds delay between the two signals. Now, you make the numbers for that, you'll find out that light and gravitational waves move at the same velocity to a part in 10 to the 15. It's just an unbelievable small number difference between them. And that difference may yet be explained by what is really going on at the source. And these are, so this was a very big discovery. And now comes another, the kicker to this, is really, which is the part that started a new field called multi-messenger astronomy. Because here is what came of it. Here's again a map of the sky. And here is the sighting a LIGO would have had all by itself, that banana and that banana. Here is the uncertainty circle for the gamma ray telescope. And when you add Virgo's information, which was a little complicated, but when you add that to it, you wind up with this little green thing right there. That's the position in the sky where this particular source was. That was enough to let astronomers with real telescopes and real pointing capability go look, and what they found was this. They had luckily had taken a picture of this region of the sky. Here is a galaxy, and here's some stars in our own galaxy. And there's a little mark there, you don't see much, but go look right after, sort of 10 hours after the event we saw. And here's the same stars as in the later picture. And there it is. There is a new dot right there, and that is the neutron star colliding with another neutron star and now you see it optically. And that started a whole new field of science. Because now what we found out is that these two neutron stars, and this is just a model, we are not yet at the point where we're absolutely sure of this. Here are the two neutron stars that come together, they collide, they make a new black hole maybe, because they can't go into, they're too heavy to make another neutron star when you put them together. Here is the direction of that gamma ray burst coming off like that. And then there is all sorts of debris in this thing which was seen, but all different classes of astronomy. Infrared, well, how much? Yeah, I think I'll make it. Thank you. She told me I have 5 minutes. 5 or 2 minutes? 5. Oh, wow. 4, okay. Well, anyway, what came of it is this is a sort of advertising picture. It says, look, here are all these different methods that it turns out the neutrinos did not see this. They will eventually, but not in this go. But X-ray radio waves were seen, infrared, all these different methods were used, and some very fascinating things came out of it. I'm going to tell you the one that was most interesting to a lot of people was a puzzle that had been around for a long time. The puzzle was that people didn't know where the heavy elements come from. What I mean by that, and this is a picture of a periodic table, the kind of thing you learn in high school chemistry, or maybe college chemistry, and you can see a color coding to it. The things that are blue are things like helium and hydrogen, which came out of the big explosion that made the universe. But then most of the other elements, and those are either green colored or yellow colored, came from the inside of cooking inside of stars. But people couldn't get the very heavy elements. You'll notice the green ones, the green ones and the yellow ones sort of quit in the middle of the periodic table, near iron. And all these heavy guys, the purple guys, nobody knew where they came from. And they come from, we now know, neutron star collisions like this one. And for example, things we know and love, like gold and platinum, all the gold and platinum that is in the universe came from these collisions. So, you know, we can't go mine it, it's too far away, but anyway. So that was one discovery, and there were other discoveries, and I won't really say what they are in the sense that there were some interesting things for cosmology. I'll leave that for the questions. Let me just say, this is 2 slides left. One is where are we going? So this is so those of you who care. This is another picture, but this has a picture of, this is a little more subtle. This is a picture of sensitivity again here, and frequency this way. So here's 100 hertz, there's a kilohertz. And here are the noise curves for different detectors. This is, for example, the Virgo detector, and this is still its noise. Here's LIGO that made the detections that we've been talking about. It's a little better than Virgo, but it doesn't have to be. Here is the design for LIGO. It's this green curve. And you'll see, to our disappointment, we have not made to the sensitivity as good as this design yet. And we're working very hard to try to bridge this distance from here to there. Then there are ideas. These are now factors of 10. Each one of these is a factor of 10. Ideas of even making it better. And then you get down here, and there are two ideas in Europe and in the United States of making new kinds of detectors that will eventually take this whole field into being able to do cosmology. That's in the future. And so here's my last slide. I want to give you sort of an overview of what's going on in the field right now. And this is, all these things that are in this picture are going on right now. And this is a picture of the frequency of the gravitational wave, or up here, the period of the gravitational wave. So, for example, here's the age of the universe. And this is years, and this is hours, minutes, tenths of seconds. Tenths of seconds. So here's LIGO, and this is the strain. And so here's LIGO with its arms, and it has the sensitivity to these things that are called compact binaries, these very little tiny nuggets of stars, black holes and neutron stars. And that's in business, and we'll try to make it better. There's another whole project to look at gravitational waves at periods of hours to minutes. And that's a space mission, which is just about as old as LIGO. It's called LISA, the Laser Interferometer Space Antenna, and they hope to see big black holes colliding with each other, and also white dwarf stars colliding with each other. And this is a space-based interferometer with a very clever design of objects going around the sun. It's a three objects, a triangle going around the sun at the distance of the Earth. In other words, in 1 AU away from the sun. This will probably be built in Europe, and it will be flying in about we hope, 2030, maybe 2032. This is a project with even longer periods of years, and this is going on right now, and this is something very interesting. This is people using radio astronomy telescopes right now and using pulsars, which are these neutron stars, and these are very fast clicking pulsars, ones that are moving and rotating very, very quickly. Maybe 400 times a second, that fast. And what they hope to do is they're all in our galaxy, and what they hope to see is the following effect due to gravitational waves. You look up in the northern part of the galaxy, and you see all the pulsars up there, they go a little faster. You look down in the southern part of the galaxy, all of those are going a little faster. And you look to the east, and all of those are going a little slower. You look to the west, and all of those are going a little slower. They want to look for a pattern like that. And what would that be due to? That's due to very long period gravitational waves, periods of years coming through our galaxy. And people are looking for that right now. They have set limits on this, but then that could come from black holes that make collisions that are 10 to the 9, 10 to the 10 solar mass black holes. And that's an active research program right now. And this one on the left is probably the most exciting one of all. And that is an attempt to try to find the gravitational waves that came from the instant that the universe was born. Okay? There are a lot of accelerations. There were quantum fluctuations at that time, and they cause the cosmic background radiation, which is the radiation that we all know about now because we can hear it on our radios, on our FM radios. Little of that hissing noise that you hear between stations on FM radio comes from that explosion that made the universe. And that's been known now since the middle 60s of the last century. But that particular radiation will have certain attributes, especially the way it points, its polarization. Its polarization will have patterns that are determined by the prior emission in the universe of gravitational waves. And that's called, they're looking for B modes. I won't describe those unless you ask me questions. There's a particular pattern of that radiation which they hope to see. And that will be one of the most interesting discoveries of this whole idea of looking for gravitational waves, looking all the way back to the beginning. Well, thank you. I should sit down, huh?
Yes.
Yeah, that'd be a pleasure. Thank you. Should I get rid of it? Well, I'd better leave this up, yeah.
Thank you very much indeed, Ray. The time of the evening has come where we're going to have a slightly less formal interview. We've got Sara Seager, who's returned to the stage.
Right.
And after they've chatted for a little bit, there'll be a Q&A opportunity. So, Sara, Ray.
Thanks, Ray, for a great talk. I'm waiting for this. Thanks for a great talk.
Yeah. Well, it wasn't so bad. What did Charles say? Where's Charles?
Charles, Comes over
He's all right. He's all right with it? Okay, good. Thank you.
So I just wanted to start with this first gravitational wave detection, which was just so phenomenal. It was a huge signal, right? Like much bigger than you expected.
Well, it was much bigger than we expected.
Can you tell us a bit about that?
Yeah, I can tell you. I'll tell you a little story.
Sure.
Okay. The story's a little crazy, and you better shut me up because I can keep being a storyteller. That's the trouble.
Yeah.
That's your job. So when we first saw this thing, all of us, we thought it wasn't real. It was on the morning of the 15th of September 2015. All of us who were in the project thought it was a blind injection. And that's the thing where we put signals in the detector ourselves to test the people who look at the data, to test the detector. Very rapidly, within a day or so, we found out that nobody was really ready yet.
But so did you have these before, like in July, previously?
Yeah,
you got these tests?
The ones I showed where we had it in the first detector.
So people would put fake signals in and they would show up?
We would put fake signals in and people would fetch them out.
But they didn't tell you, right?
What?
Did they tell you, like, here's a fake signal?
No, you never tell. Yeah. You never tell. It's a way of testing everybody, okay? The person who knew about the blind injections is the head of the project, okay? And you give a little telegram to him or her. So anyway, that was not the problem. So the next thing was really quite awful, and that took us almost 5-6 weeks to get out from under. All of us said, wow, it's too big, and we don't believe it. Maybe we've been hacked. Okay? Well, that sounds kind of innocent, but it turns out hacking is something nowadays you have to think about. And that took a long time to get out from under, because you could every day, as when you started, and people did the sort of things that you would expect. You look in all the different parts of the signal. Look at the beginning, where it goes from the detector right to the amplifiers, from the amplifiers to the digitizers to the tapes, and so forth. And you look, is the signal the same, and so forth and so on. All of that was in order. But every day you would come up with a new hypothesis how smart those hackers were.
But who do you imagine would be...
They were always smarter the next day.
But who would you imagine would be hacking this?
Yeah. Well, no.
Yeah?
People could have... You see, we had a bad history to deal with. Mr. Weber's history was not a good history to deal with. So we were very, very worried. And in the end, it's sort of, thank God, some of us really didn't want to publish. And we waited and waited. And thank God what happened is some other black holes showed up. That helped a lot. Yeah. And that finally gave several
confidence,
the courage to go ahead.
Right. But this signal was so massive because the two black holes, I think they were more massive than people expected. Yeah, in fact, I can go show that on the slide. There's an interesting viewpoint to that slide. They were bigger, yes, than most black holes people had seen in X-ray astronomy, and you had seen them yourself. Were sort of 10 solar masses, maybe 12 at the biggest. This was 30 solar masses, a pair of 30. And that's still kind of a mystery where they come from. That's the thing that we will find out as we go deeper into running this instrument. Well, it's a great thing about observational astronomy, so to speak, that you see things you didn't expect. So once you saw the second one or the third one and you were sure it wasn't a hacker, how did you feel about this? Was this like super exciting?
Well, I tell you, some of us felt a certain relief that we hadn't just been, that we hadn't used all the taxpayers' money for a total mistake, But there was some relief. But the thing that most of us thought about was that we had done something kind of interesting. And it had not to do with the detection of gravitational waves so much. I mean, yes, the newspapers made a big fuss about, another piece of Einstein now has been shown. People had already, as far as I was concerned, seen Einstein's gravitational waves with Hulse and Taylor. What was seen is all of a sudden you have another way to look at the universe. And that was new to all of us. We suddenly had said, oh my God, we can now look in a completely different channel, a channel that has never been tried before, namely using gravitational waves. And we're going to see we're going to see old things in a new way, like black holes. But we're also hopefully going to see things we never even thought about. And that has been sort of the tradition in astronomy for years and years. Every time you open up another wavelength, or in electromagnetic astronomies, you find something new. And that sort of is slowly dawning on all of us now. We've started a field. Yeah.
Wonderful. So there's something like 1,000 people in the LIGO collaboration. So once you all realized this was a real thing, how on earth did you keep this a secret from like September till the next February? Because no one had heard about this.
I don't think it was very well kept. I think there were people guessing at it. Larry Krauss, who has gotten into disfavor for other reasons, guessed at it pretty quick.
But it didn't make it out so far,
No, I'll tell you why. It would have been a violation of a certain trust we had in each other.
For 1,000 of you all trusted each other.
Yeah.
Oh, it's amazing. Okay, so I want to back up a little more, like much further back, when you showed Kip Thorne and he gave you the number, the very, very tiny number, and you realize you have to build something on the order of 4 kilometers. Like, how did other people, you know, that's kind of like a sticker shock. It's like, wow, 4 kilometers. Eventually you got used to that number, but how did the other people around you feel about that number when you went to the, you know, to fundraise or to NSF or wherever, and you said, look, it's got to be 4 kilometers.
Well, okay, that's a harder question, a much harder question to answer than the others. What she's asking really is how did this evolve from what I would call tabletop science into what might be called big science. I think that's really the question you're asking, I think. And it turned out that was not a trivial thing. It was hard on the people within the project, and because you had to have more discipline. I mean, and in fact, we went through various phases of not knowing how to run a project that was of that size. And that's one of the reasons why, for example, I have absolutely no misgivings about Barry Barish, who won the Nobel Prize along with Kip and me, that Barry pulled off a very, very hard thing to do, to take a group of people who were independent and always on their own and make them work together. That was a part of the thing. That was the beginning of it. And you couldn't do this without having a discipline because you were now really spending big money. Now, why did we succeed all through all the different phases of the project? Now, mind you, the NSF, the National Science Foundation in the United States, began to support this thing in the middle 70s. And we made our detection in 2015. So 40 years pretty much. And it turns out there was what I call a mole we had in the NSF. We had a person in the NSF who was very much for this and was much better, even better at describing all the wonderful things that might happen if this should work to the people in the NSF and the Congress and the people who were important. He was a devotee of this whole idea. He himself, his name is Richard Isaacson, and he deserves an enormous amount of credit for having kept this in the mind's eye of the NSF, even though at the time when this all started, and this is, I think, I'll be honest about it, we were not sure the technology was really going to make it, and we were not sure of the sources. All we knew at the time was supernova. We hadn't really thought the thing through enough. And nevertheless, it was a big, big gamble the National Science Foundation took. And he made them understand the gamble and made them take it, which is very interesting. I don't think we can do it again. We happen to be lucky, you know? Yeah.
Well, it's amazing that you thought you were going to find supernova explosions, and now that's sort of not happening. You're finding these black holes. Yeah, oftentimes these big new observatories, you have one motivation, anything to get it motivated, and you end up finding something else. Well, I want to switch gears a little, and everyone here got to hear about gravitational waves. But what if the Ontario Science Centre could make an exhibit on it?
Say that again?
You told me before in Louisiana, there's like an exhibit, a science museum exhibit kind of thing. What do you think the Ontario Science Centre should do? They could have an exhibit. What would that be like? Oh,
okay. No, she's talking about, what Sarah's talking about is something which I'm very pleased about. The state of Louisiana, which is, most of the south of the United States does not have good schooling. It's just an unfortunate thing. It's not well off, and so consequently, since we support our schools through taxes, they don't get good schooling in much of the South. And luckily, the state of Louisiana and the federal government, in our case, the National Science Foundation, decided that it was a good idea to fund an outreach center. And that's what Sarah's talking about. And if you ever go to Louisiana, you will be able to go to this and visit it. It's a thing that was funded both by the state and the federal government. And it has in it a whole set of experiments that are things that you saw in my talk, the vibration isolation systems, the interferometer, the layout of the interferometer and how it makes the light go dark and bright. Virtually everything I talked about has a little example of a real experiment that you can play with in the outreach center. And the way that works is that schools from all over Louisiana, these are now high schools and grade schools, bring their kids in big buses. The teachers come to these things, and the teachers, while the kids are playing with the experiments and learning stuff, the teachers are being taught by the staff we have at the outreach center on how to make the devices or talk about the science that we're doing, but mostly the things that are in the outreach center, so they can take those and make them at home and make them exhibits and also experiments that the kids can do at home. And that turns out to be an extremely successful thing. Yeah.
I thought people might also, in our earlier conversation today, you were telling me about some maintenance issues on the LIGO. I was wondering if you could share any of those.
Well,
because they're not the problems we expect when we hear you're going to.
Oh yeah, well look, I mean, you build I know what she's referring to, that Yeah, this is just a problem. We built these systems. You saw those vacuum tubes in the picture. You know, those big stainless steel vacuum tubes? Well, it turns out in the south, we have a problem, which we don't have in the north. There are bacteria. This one will shock you, but the Navy knew about this, but I was not privy to the Navy's knowledge. But there's bacteria that eat the stainless steel. And the way they do it, there are a pair of bacteria that do it. I don't know the names of bacteria. You have to look it up. By the way, the stuff is called MIC, microbial corrosion. And it's a thing. It's a whole topic you can find out on Wikipedia. And what it is, the ones that do the job on us are one bacteria that eats the chromium oxide, which is the thing that protects stainless steel. And the other one follows the guy, and he squirts or she squirts, or maybe whatever it is, squirt hydrochloric acid or sulfuric acid on those spots where the chromium has been eaten off. And that makes holes in the vacuum system. And that we didn't know. It's now, the vacuum system is what, 17, 18 years old? And we're now very worried about that, and we have to dehumidify we had to dehumidify all those concrete covers that you saw over the tubes. They have to have no water in them. Otherwise, we will continue having this problem. In the Pacific Northwest, we don't have a problem like this. So anyway, that's a sort of an anecdotal
amazing,
thing.
Really, I know. Are there any other anecdotes that you could share with us about major challenges like that we wouldn't have thought of or wouldn't know about?
Well, the big challenge in the end was trying to get it. Let me say something about the challenges. And this is not to make it to denigrate your question. I don't mean it that way. All of us who were working on this thing enjoyed the challenges. You have to understand that. It wasn't that every day, and people have asked me this question over and over again, not quite the way you have, but and I'm saying yours is more gentle. But what it was is they say, oh my God, I'll give you sort of the extreme example. Somebody says from the press, says, oh my God, how you poor guys, how could you have lived so long without a result? How could you have, and so forth and so on. And how do you survive all of this? It isn't that way at all. It turns out, how is an experiment like this done? It's done with a bunch of friends of yours, first of all. Most of us get along very well. All the people at MIT who worked on this thing, all the people at Caltech and MIT together, they worked as a team, and they really enjoyed each other's triumphs. So, and what happens is every day, what keeps you going is, oh, you're working on a new problem you have. All of a sudden, here's this piece of electronics that you would design, it doesn't work. Suddenly it works. And then you say, hey, come over here, look at this. And you look at it on this, see this, it does exactly what it's supposed to do. Hey, let's go out and have a beer. You know? And that's the kind of thing that keeps you going. It's the daily encouragement you get from solving one problem after the other. And that's really the thing that most people don't understand about the process.
Yeah, it's so true. For science, it's just that thrill of just finding something out or getting something to work.
Yeah.
It's so great.
And dealing with people who enjoy each other. That's very important.
Yeah.
I mean, enjoy each other's triumphs. What I mean, but somebody else was working on something else. And they would say, hey, take a look at this new isolation system I just built. It really stops that mirror from shaking. I said, oh, wow, that's really great, you know. Let's go have a drink on that one. You know?
Another thing I wanted to, we only have a couple more minutes for
this.
Sure,
go ahead. Yeah.
I just wanted to share another thing with the audience, that more than one of my friends now, who has been an undergrad at MIT a long time ago, said, wow, Ray saved my bacon. These were like someone who was failing junior lab, someone else who failed their physics qualifying exams, and these people are grateful to you for helping them.
Well, you gotta do that. So do you.
Yeah, but the way they tell the story, you went above and beyond. So
no,
I just
don't
want
think
people to know
you
about
watch.
that.
All the faculty have to do that. You have to drag people along when they get in trouble. Yeah.
So my last question, actually, it's a little out there, so I just want to, you showed all these amazing things that may happen in the future if we can get down the factor of 10, 40, 100 or more.
Yeah.
Will there ever be a day when we have so many gravitational wave detections that it's going to be hard to pick one out from the other?
Yeah, well, she asked a very good question, and in fact, that may yet happen to us, even in the 4-kilometer system. Right now, we're not running right now because we're trying to make up that gap between where the detector is to where we think it ought to be. I showed you that in that picture. You may not have caught that, but that was intended just to show you that we have work to do with the detector we now have installed already. And if we get that, we get probably a factor of 2. Now, what does that factor of 2 mean? Let me try to explain that to you. Right now, we're seeing about 1 black hole event per month when we're running. And we see probably 1 neutron star collision a year right now. And if you can improve the detector by just 2, that means you can look twice as far into the universe. And the reason why you can look twice as far, we measure the amplitude of the signal. We don't measure the power in the signal. For those of you who deal with optical telescopes, you always make a telescope, you calculate its power by looking at the amount of intensity that you can measure. Smaller intensity. We don't talk about that. We talk about the square root of the intensity, which is the amplitude of the field. And so consequently, when you make an improvement in the detector by 2, you're talking about measuring the amplitude of those signals that you saw in that picture with twice less noise, half the noise. That means you can look twice as far in the universe for the same signal and get the same signal of noise. Now, what does that mean in terms of the rate of signals? Well, when you look twice as far in the universe, that means you're looking into a new shell of a spherical shell that has a volume that is 8 times bigger, not twice bigger. The shell is thicker by 2, but the volume of the shell is 8 times bigger than what you had before. So we won't have just an event every month. We'll have an event every half a week. And by another factor of 2, it gets to the point where we're getting events per day. And we're hoping to go another factor of 10 eventually. So you're having events every hour or every few minutes.
Wow,
yeah.
That would be amazing.
Sorry, say again? I couldn't hear what you said.
She's going to cue you guys to do questions.
Oh, you'll run out of beer.
What?
He said you will run out of beer.
Yeah, out of beer. Thank you.
Thank you.
Well, we'll have to come up to Canada to get Molson.
Okay, thanks, Ray. We're now going to move into the Q&A from the audience.
Can we turn the lights up so that we can see the people? Is that possible? Hey, thank you.
And I'll be moderating. So let's see, where are the 2 volunteers with the microphones? So if you put up your hand, I'll choose questions as we go. Let's start here, in the middle here with the black. Yeah.
What was the total cost of the LIGO project in the US, the 2 locations? And secondly, is it true that the FedEx trucks pulling up to the shipping dock sometimes look like black holes?
Well, I'll answer the first one. I don't know about the second one. The total cost of the project has 2 pieces to it. One are the 2 investments that, now that you saw this talk, well, the first investment was making the facility and the first detector. That was about something around $180 million in 1994 dollars, in American dollars. And then the second go-round, after we had demonstrated that we were able to get the thing to design, there was another about the same amount for making the second detector. We didn't have to build the facilities over again, but we had to put all these new guts inside the thing. So right then, and then so that's another 180, so we're up to 360. And then on top of that, it costs about $50 million a year to keep those facilities running, and people and stuff. So we have spent about $1.1 billion over something like 15, 16 years.
Okay, next question. Okay, right there, the girl in the purple shirt, right there.
Hi. So I looked at the what's this called again? LIGO website, and I saw that it was 6 observations, and I saw only 4 on your presentation, and I also saw that there was only 1 neutron star collision. Why is there so little?
Okay, can you help me with that? Yeah.
So first was just a comment that on the website it shows 6 detections, but your talk only talked about 4.
Okay.
But her main question was, why is there only 1 neutron collision?
Right.
Why aren't there more neutron star collisions?
Okay. Well, it turns out that I'll say something to you which is probably a little bit secret, okay? But it's now going to be announced very shortly that we have probably seen 10 black holes. And that's going to be mentioned in a paper that comes out in the next month or so. And those was where reanalysis of the data has made it so we've probably seen 10 black hole pairs. But we've only seen 1 neutron star pair. And that is something we didn't know. We had no idea how many of these things there would be. when we started this whole experiment. And so now we know, and we now know, for example, if we do improve the apparatus, for example, if we improve by 2, we're going to see 8 events of neutron stars per year. About.
But Ray, do we know why, or is that an answer for the future?
No, that's looking at what we have now.
But do we know why that there's so few neutron stars?
Oh, I cannot tell you. No, that's another problem. Why are there so few of these? Now, the thing is, you have to look at where they might come from. And let me give you 2 things. We don't know. A lot of things you're now asking, we don't know the answer to. For example, when people guessed at how many neutron star pairs we might see, and that was the only thing we really thought we could calculate. People guessed at the number that we would see with the sensitivity we have now. They guessed, in the papers that were written by reputable scientists, they guessed somewhere we might see 1 every 10 years to something like 10 a year with the sensitivity, but people just didn't know. And the reason is they didn't know quite the mechanics of how nature makes these black holes. Most likely they're made by supernova, a star that collapses, and then for reasons that this particular star, most of the time they don't do much. They just collapse and they make something, either a black hole or a neutron star, but the occasional ones make 2 black holes, and occasional ones might make 2 neutron stars. And people couldn't really make a good calculation for that. So now we know a lot more than we did before. Now with black holes, the most likely sources are not, the sources for neutron stars are most likely imploding stars. And that's still probably everybody's best guess. On the other hand, for black holes, there are a lot of different ideas where they might be coming from. And here are the 2 ideas that are most prevalent. One of them says supernova, a star that's very big, collapses, makes 2 black holes. But that isn't the only way. You could also make them in something called globular clusters. These are places in many galaxies where 10 to the 9, that's a billion, or even 10 to the 10, stars live all together in a place. And they collide with each other, and they start accreting with each other and making black holes. And that's another place where you could get binary black holes made. And right now, there is a way we could separate those 2 processes by looking at the spins of the black holes. And if the spins are the same or about the same, we probably think that it would be common envelopes. It would be out of a supernova. But if the spins are in all different directions and different magnitudes in these binaries, it probably is what we call dynamical evolution, which is this latter way. So this is a new field. We don't know enough. And so we now know.
A great question that there's no really solid answer to. So nice work. Okay, next question. Let's come over to this side here.
Oh, thank you, Professor Weiss. You did a great job explaining the physics. I'm more interested in hearing some personal stories. I mean, you've spent time in the astronomical and physics academic community. Do you have some stories about some of the more colorful characters, Richard Feynman, Murray Gell-Mann, maybe?
No, I don't have a lot of colorful. I have colorful stories about people who I worked with, if that's what you're after, but I don't want to retell them. My own life was speckled enough, I have to tell you that. I flunked out of MIT as a junior. I had a love affair, okay? And I didn't care about school very much. And then the thing that saved me was I ran into a man. I've told this story to somebody already today. The guy who saved me was a guy named Gerald Zacharias, who I worked as a technician in that lab. I noticed in one of the things you had as the teasers for my talk was that I'd worked on electronics as a kid, which is true. That's where I learned. I would call it street electronics. You know, electronics you learn out of popular science and popular mechanics and things like that, but not really deep knowledge of the equations that go with the electronics. So I built a lot of stuff, and I was a ham and all that stuff that you could be as a kid. And I went to school to learn how to do that better. And then what happened is I had a skill when I flunked out. I became an electronics technician. And this man had a very interesting set of things in his, and I'm giving you this story so you can see the evolution of me, which is probably the only thing that I can really talk about authoritatively. And that is that he was working on atomic clocks. That was what that lab was working on. And he wanted to do the experiment of looking at the fact that clocks in strong gravity go more slowly than clocks in weak gravity. And in fact, we worked on that experiment together for a couple of years. And I was a technician and he was the professor. And eventually he said to me, well, you know, you ought to go back to school. So he got me back into school, even though nobody at MIT would have ever thought they would take me back. And they did, and then he got me through graduate school. And then later on, he even got me a job. So, you know, you need a guy like that in your life.
Okay, next question.
Enjoyed your talk, sir. I'm a bit worried. You got some problems with the Louisiana bugs. I was wondering, how big is the problem from the White House?
From the what?
White House, he wants to know.
I mean, you have a long trajectory for your experiments, and the White House is oscillating at a much higher frequency than your trajectory.
Okay, his question is basically about budget. Let's just say, the administration, like, are you still getting enough money for the project? Or is the weird politics in the US?
Okay, in other words, is the National Science Foundation budgets interfered with by your President Trump?
Okay, thank you for that question. I had trouble understanding exactly what you said. And it's partly my hearing, okay? No, the National Science Foundation, we have made them feel very proud of what they've done. And I think they should be very proud of what they did. The National Science Foundation, just think, they took a project, and because of this mole we had, but that wasn't the whole story, they took a project which was sort of embryonic and not terribly well thought through, okay? Helped it along. It went through various vicissitudes of its own. We had trouble with getting along with each other at the highest levels, not at the level of working in the labs, but at the level of organizing it. And then eventually you had the directors, and some of the directors didn't do so well. They kept this thing running and going for a very long time. And what they did is they eventually won a gamble that they took, a big gamble they took. And I have been to Congress, I've been to the Senate, and I've explained to the Congress and the Senate, people who want to listen to this, that this is a fantastic story about the way science, you have to always keep a little bit of a budget, some budget for things that are not sure bets. And I'm trying to make that the story of how you keep supporting science. And that, I think, when you tell the story of LIGO, and ultimately its success, it turns out they begin to listen. In other words, there should be in any budget, and this is the kind of story that you tell when you go to, and NSF is very much behind this. They say there should be some fraction of the budget that should go into speculative science. So science that is not absolutely assured that you're going to get the results that you say you're going to do. And I think if we can win that, science will be in much better shape than where everything is analyzed to the point where nothing gets done because, oh, there's always this question, can you really do this? Can you make it happen? Oh, no, we're not sure that, no, we don't want to put it, we're too scared of making a mistake. And that's the way they kill science. So that's the mess, and NSF is willing to listen to that.
Okay, question here in the front.
Hi, so, hello?
There you go.
Hi, so one of my questions was at the beginning when you explained how you can only measure non-spherically symmetrical objects, which means if you had a spinning black hole, it wouldn't produce gravitational waves. But I do recall reading that spinning black holes or high masses can like frame drag and kind of drag space-time around with it, which would also produce gravitational waves.
No, be careful with that. What you're asking, he's asking a fairly subtle thing. There's a thing where if you have a spinning object, like the Earth's spinning, or a black hole that's spinning, it makes you can think of it making a magnetic gravitational. Do you mind if I use that analogy? I mean,
sure, yeah.
It's and in fact, there's been an experiment done to see this, to show that when the Earth spins and you have a gyro in orbit around the Earth, there is a precession. That gyro, there is a spin-spin interaction, a spinning gyro magnetic spin, gravitational magnetic spin, interacts with the Earth's gravitational magnetic spin. That interaction has been measured now. And it's called the lens steering effect, among other things. And the thing is that it won't radiate gravitational waves. It doesn't, because there is no time-dependent, I'll say it's a fancy word, but there's no time-dependent quadrupole moment. A quadrupole moment is a thing where You go from one kind of ellipticity into another ellipticity. And that's why you have to have something, a spherical thing that doesn't change shape, has the same cancellation in general relativity as it does in Newton. Remember, when you do Newton and you calculate the gravitational field of a sphere, you can completely forget about the sphere and just calculate the whole mass being concentrated at the center of the sphere because of the symmetry of the problem. That same kind of calculation happens in general relativity when you look at the source of the gravitational wave. If it has no asymmetries, if it has no cancellations of the gravitational waves from the different parts of the sphere. That's why there aren't any. So it's a symmetry problem. That's what's causing the thing. So a spinning black hole or a spinning object does not radiate gravitational waves either. I think that's what you asked.
We're going to take one last question right here in the front.
These discoveries are all very exciting for the for astronomy and people who are interested. I wanted to ask how you get people who aren't interested in astronomy interested in these discoveries.
It's a hard question. I mean, I think the people here are trying to learn how to do it too. I mean, the people who run the center and people who are teaching science are trying to learn how to do that also. I guess I have my own theory. I mean, and this is not from any educational theory, or it's just from my observations. I go to grade schools a lot. I love to go to grade schools and teach kids. You know, I've always come with some sort of experiments. Polarizers are a wonderful thing. You bring a whole bunch of polarizers, give them to all the kids, let them play with it, and you can do all sorts of different things at different levels. And it turns out that the way you get people to be excited about science, whether it's astronomy or it comes through discovery. They somehow, when they get engaged and they see something for themselves, that is far better than going to the blackboard and drawing it or telling them a story. Let them see it for themselves. And for example, I know one thing. Once you have shown somebody how a rainbow works, make an experiment, you know, with a water drop, and put light onto the water drop and make it big enough so you can see the actual trajectories. People will never forget why a rainbow is the way it is. And once you tell people about, and show them, for example, in a gas, that when you shine yellow light into a gas from the side, you know, a blue light into a gas, it shows yellow when it re-radiates it. That's again the same kind of thing that happens when you have so you can explain why we have a sunset that is orange. And the more that you can put in front of somebody to see it for themselves, the more engendered people become with the science. What people see, most science is taught in a bad way, I think. It's taught through mathematics. That's not the way to do it. Mathematics is a handmaiden. You want to show the phenomenon. That's just my feeling about it. I don't know how to do it. And seeing, for example, Saturn's rings through a telescope, that's right in front of you, and then you can adjust and you can see the gaps. I mean, it's a heart-rendering kind of thing. You would never forget it. So it's the experience of seeing and hearing and doing. I don't have a better answer. That's the best I can do.
Okay, and before we wrap up for the evening, we have Charles Darrow here to thank the speaker.
Thank you, Sarah. Before I thank the speaker, Ray, I have to thank Sarah, my wife, for honoring me this way. It's it's a difficult thing for me, a humble person I am, and it's kind of the Schroeder the cat thing. I'm embarrassed and honored at the same time, and depending on when you ask me, you'll get different answers. But before I thank Ray, I'd also like to thank the Ontario Science Centre for hosting us and hosting the RSC meetings for the past many, many years. Sarah and I were just talking there, fond memories that we have as young kids coming here, and the joy that we had in discovery of tinkering with the stuff in the communication hall, and I still remember docking spaceships and things like that. And I just wanted to say that if any of you have any curious children, nephews, nieces, and all that, bring them here and cut them loose. Or if they have an interest in astronomy, have them join the astronomy club. I happen to know a half-decent one. And anyone around that you see with a blue tag on, you can ask them about information about it. Another thing I just want to say, and I said this at the last lecture last year, is that, that everything that we have around us here that's not natural we have it because somebody was curious. Somebody tried to figure something out. And, it's like a cell phone that some of you are probably looking at now because you're bored of what I'm saying. But, and so it's people like Sarah and people like Ray that were curious and are curious, and they've given us, now Ray's given us a new way to look or listen to the universe now. And this has opened up a whole new field, and that field is going to be needed to be filled with new scientists to continue this legacy. So motivate your children. Science is cool, it's not nerdy, and nurture them along. So at this point, I'd like to thank Ray for his most captivating talk. I didn't scour at it, and I really, it was a great talk. So we have a nice little honorarium for you and a calendar from the RASC. And I decided that for these talks, I would try to give you something, a little bit of memory of Canada. And it wasn't going to be, unfortunately, Molson beer. Apparently, you might need a lot of it. And but there's a set of coins that the Royal Canadian Mint struck with science on it and some astronomy, and so I picked one up for you, and it glows in the dark. So,
really?
So I'd like to present that with you, Ray. So thank you very much.
Oh, thank you.
And I'd like to thank everyone else for coming.
Oh, my. Thank you very much. So it wasn't a disaster. Not a disaster, okay. Oh, wow. Wow. Well, thank you very much. It's a pleasure to have been here, and I enjoyed you enormously. I'm welcome to anybody. Welcome. I'll stick around to answer questions.